Hello friends, with this video I will give a short introduction to a homemade magnetometer which is able to measure magnetic fields. And here a short explanation of the principle. We have a loop which is in some area and moved to a magnetic field, or the magnetic field is moved to this area. Thereby a voltage is induced into the loop, and the integral over this voltage over time is proportional to the flux change, so the magnetic field times area in the loop. And if you measure the integral and divide it by the effective area of the loop, we can compute the magnetic field, the magnetic flux, the magnetic induction, if you want to be exact. We can make the area larger by having a multi-turn loop, namely a small coil. Schematic starting with the probe coil, namely the loop, which goes into an integrator consisting of an operation amplifier, a resistor and a capacitor, followed by a further amplification by a factor of 100 going into an analog digital converter, going to a microcontroller. The microcontroller, on the other hand, also controls the digital analog converter, which is used to fine-tune the offset value of the integrator by a reduction factor of 1 million. Here. Further, we have a discharge relay which discharges the capacitor, controlled by the microcontroller, and a potentiometer which is used to communicate the sensitivity of the sensor to the microcontroller, read by the analog input of the microcontroller. Now let's start the instrument. We switch it on, and it starts with the auto zero sequence in 5 iterations, now shown in time lapse. In between the iteration steps, the applied offset voltages are shown. As you can see, it's about 0.1 microvolt. It's refined a bit. We have to get rid of all the thermo voltages and whatever else disturbs us. So after the last step, we are ready to measure, and hopefully the integral now stays constant, at least as much as possible. And now we demonstrate the effect of putting a small neodymium Bohr magnet on top of the probe coil, and we measure field strength at the surface of the magnet of about 2000 Gauss. We can remove it and reverse it, then we have the negative value. Remove it again, we come close to zero, not exactly, we have some microvolts. A bigger magnet gives a bigger field, of course. And reversing it with reduction due to this not so strong black ferrite block. And now we demonstrate the effect of a steel plate which is in between. The sensor is in between the steel plate and the magnet. You get a huge increase of the magnetic field in the probe coil, of course, even about 7000 Gauss. It's hard to remove the magnet from the steel. Yeah, again with the ferrite block in between, the field is a little bit lower. And Finally, I want to show a more sensitive arrangement. It's just a more sensitive probe coil with larger area, about 2000 square centimeters effective area. And even after 1000 seconds, it's only very little offset after long thermalization. And okay, we discharge several times. There's always a little offset. Okay. Try again. That's as far as we can get. And now I will show the approach. First, off screen of a neodymium bore magnet, and you see already the display moving, and after a while the magnet will become visible from above. And now even at 20 centimeter distance we get a accurate reading of the field. Remove the magnet again and we are back to zero, more or less. Another magnet, reversing it and removing it again. That's it. More in this Electra project page shown in the URL.